Okay, so we're going to finish up the Doppler effect in this video. Well, by popular demand, people have requested this Doppler effect video, so have at it.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow.
Terrific.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Alright, anyway, back to business. So, yesterday we went over this, and we actually did some review on page 40, went through the Doppler effect. And essentially what we said was, with our little starship demo, if there's no relative motion between the source, which could be a light source or a sound source, and the observer, then everything seems as it should be. Whatever frequency light this is giving off, that's what the spaceship sees. Whatever frequency sound this is giving off, that's what the spaceship hears. However, once you put things into motion, you actually get this Doppler effect. And the easiest way to keep this in mind was to simply say, imagine that as things move toward each other, it doesn't matter if it's source toward observer, observer toward source, or both toward each other, as they move, as they approach, you can imagine that the waves somehow get squeezed between them. Really what's happening is that the observer is intercepting new wavefronts at a higher rate. But either way, they get more squeezed, and it'll look something like this. Let's do the observer approaches. So the waves are closer together. That's higher frequency, smaller wavelength. But as soon as they start receding from each other, whether it's the observer away from the source away from the observer, or both away from each other, you then have, you can imagine in your head, the waves in a sense get stretched out. Really what's happening is the observer is intercepting the wavefronts less frequently. And you will have a smaller frequency and a bigger wavelength, which you'll see down here in the graph. There it goes. So for someone on the ship, someone who is an observer, this is a very real experience. In fact, the light would appear to be lower frequency, bigger wavelength on this side, and back when they were approaching, the light would actually appear to be higher frequency, smaller wavelength, which we see as changes in color, and this is sounds, changes in tone. So anyway, we went through a few possibilities here. You did a little homework on this last night, and one of the periods, question 122, period 4, how does the frequency seem to someone with the source? Well, if you're with the source, there's no relative motion. If you're driving the fire truck, if you're somehow on this star, then it's unchanged. There's no Doppler effect noticed there. Alright, the other thing we said was, right here, the amplitude also changes. So as things approach, they get louder. As they recede, they get quieter, or brighter and dimmer, except this is not the Doppler effect. Alright, so let's jump ahead a bit here. I'm going to skip 41 and 42, which I'll make a separate review video for those. This is really just review. Let's jump over to 43, talking about why the Doppler effect is useful. So basically, the Doppler effect can be used for a number of purposes. One of the purposes actually is with radar guns for police. So a police officer on the side of the highway, we're on page 43 now. Come on now, 43. So a police officer on the side of the highway aims a radar gun at vehicles. The radar gun sends out an electromagnetic wave that goes and strikes a vehicle. reflects and returns to the gun. Let me give you a little idea of what's going on here. So here's a quick cartoon of it. A radar gun sends out light. That light hits a moving car. It reflects off of the moving car and comes back toward the radar gun. So radar gun is not just picking up, it's actually sending out a signal which has to reflect and come back. This is why police sometimes have to really aim through an eyepiece and make sure that they're sending the signal at the particular car they're interested in and that it comes back to them. Okay, so here's another graphic of police radar. So they send out these black wavefronts. It has a certain wavelength. Of course, it diffracts, it spreads out, but part of it strikes the car, and often they aim for, believe it or not, your license plate, because it is flat and shiny. License plates shine nicely at night, more so than the rest of the car. Well, they don't just shine in visible light, they're highly reflective for the types of light that the radar gun is sending, and typically they send microwaves. Don't worry, this is not going to cook you. Anyway, it strikes the front of the car and you get a reflection back. And those are these little dashed purple lines, wavefronts. Notice the spacing there is a bit different than the spacing of the incident wave. So the incident wave and the reflected wave have a slightly different wavelength, slightly different frequency. The radar gun can actually pick up that difference, and there's a pretty easy math equation which you can look up, part of the bonus on W816 page 4, and run the numbers. This automatically does it, and you can translate that into a speed of the car. Okay, so let's go check this out over here. What frequency will the sensor read if the electromagnetic waves strike a stationary car? Well, if the car is not moving, and let's assume here the policeman is parked on the side of the road, so if the car is not moving and the policeman's not moving, you have no, there we go, get the right size. So we have no relative motion. So we have the unchanged frequency. No relative motion, unchanged frequency. So this will give back the same as the frequency as the policeman sent out. Put that in green. No relative motion, unchanged frequency. Okay, now what if the car moves toward the officer? Well, if the car is moving toward the officer, it's just like this situation where the observer approaches. So the car is moving toward the officer. The officer, in a sense, is sending out these waves just like the star. And the car is going to intercept them more frequently and actually reflect them back more frequently. So your picture looks something like, for 132, actually looks something like this picture here. And of course, it's going to intercept them more frequently, reflect them back more frequently. So you are actually going to get an increase in frequency. Now this actually has a special name for it, and I'm going to show you over here. If you look in your reference table, you will find that on the electromagnetic spectrum on page 2, that we tend to talk about these increases and decreases in frequency in terms of color. Well, this will load at some point. When that does load, I'll show you. An increase in frequency we tend to call a blue shift. The reason being, so we'll make this blue. There we go. The reason being, blue is actually higher frequency among the colors, and so when things move toward a higher frequency, the car approaching the officer, then we tend to call that a blue shift. Now, if a car accelerates away from the officer, well, first off, it's moving away. So you're going to have a decrease, not an increase, but a decrease in frequency, except this is not just a decrease. The car is accelerating away. So this is decreasing frequency, meaning it is becoming not only lower frequency, but continuing to get even lower still. We call this instead, the lower frequency color, red. We call this a red shift. So we'll make that red. Doesn't seem to want to load it. Let's check it out over here. Maybe we can get a little bit of physics reference table action. Sometimes Firefox is our friend. Sometimes Chrome is our friend. Sometimes none of the above. So let's try this out. I have more hope. Anyway, as that's loading, let's go over here. A car moving away from the officer. Well, it is moving away. It is receding. So you are going to have a lower frequency, but it's moving away. And now we're not saying it's accelerating away, just moving away. So it's moving away at a steady speed, it's assumed here. So it's a decrease in frequency, something we also call a red shift. And finally, a car accelerating toward, well, it's approaching. So you're going to have an increase in frequency, but in fact, because it is accelerating, you are going to have increasing frequency, again, your blue shift. And so, we'll come back to that in a moment, but here on PRT2, among the visible lights, yes, violet is the highest frequency of all, but for whatever reason, maybe the one syllable, this is called a blue shift. That's the higher frequency. Red shift, you can see the numbers, is lower frequency. Of course, with that red shift, lower frequency goes with a bigger wavelength, higher frequency goes with a smaller wavelength. Here's a nice extra credit. Can a radar gun determine your speed if it is pointed perpendicular to your motion? Now, another terrestrial or earthly use of radar guns is not just the police radar, but also for weather. And there are a couple questions on the homework about this as well. Basically, there are weather systems. One of them is called Doppler 4000. And what it does is it actually sends a strong microwave signal, just like the radar gun does here for the police, but a stronger signal, out into the lower atmosphere. And like any wave, when it strikes a new medium, you have transmission, absorption, reflection, tar. And so some of that wave will reflect. That's the part we're interested in. So it sends a pulse out, and when it strikes a new air mass, and remember, a new medium could actually be air at a different temperature. So if we have, for example, warm air here and cold air here, when the wave strikes that cold front, something you learned about in earth science, when the wave strikes the cold front, some of it will reflect back. Now, if it is moving toward you, toward the radar machine, you know that you'll get a, like here, moving toward, you'll get a blue shift. So the frequency will actually return back to Doppler 4000 with a higher frequency. And so then you can simply say, oh, look, the cold weather or the clouds are coming towards us. If you get a red shift, a lower frequency returns, you say, oh, it's moving away. And this is how weather forecasts are made. Well, we know what type of weather is coming, and we know actually you can figure out the speed at which it's going. Just like the police do with the radar gun. Again, this simple equation at the end of W816. And from that, you can make predictions about what the weather will be over the weekend, and so on. Okay.